In this lesson, we're going to focus on the basics of acids and bases. So one of the first things that you need to be able to do is you need to be able to identify an acid or a base if you're given the chemical formula of it. Acids typically have a hydrogen in front of them. So HCl, that's hydrochloric acid, HF, hydrofluoric acid. As you can see, there's a hydrogen in front of it, or acetic acid, HC2H3OH. Those are acids. Bases typically have a hydroxide ion, like NaOH, KOH. Those are bases. If you see a hydrogen next to a metal, like sodium hydride, then it's a base, not an acid. But if the hydrogen is attached to a nonmetal, typically it's an acid. So whenever hydrogen has a positive charge, it's an acid. But if the hydrogen has like a negative charge, then it's a base. Acids tend to be positively charged. Bases are usually negatively charged. Now you need to understand the Arrhenius or Arrhenius definition of acids. Acids are basically, they're substances that release H plus ions into the solution. Hydrogen ions are equivalent to hydronium ions in water. This really doesn't exist by itself in water. In fact, it's actually bonded to water, and so it exists as H3O+. The Arrhenius definition of bases is that a base releases hydroxide ions into solutions, while acids, they release H plus ions into solution. So keep that in mind. Now you also need to know the Bronsted-Lowry definition of acids. Acids are proton donors. Bases are proton acceptors. So let's say if we put hydrochloric acid in water, what's going to happen? HCl is the Bronsted-Lowry acid. H2O is the Bronsted-Lowry base. The acid is a proton donor, so HCl is going to lose the hydrogen and turn into chloride. The base is a proton acceptor. Water is going to accept the H plus ion, and it's going to convert into the hydronium ion. This is called the conjugate acid because we added a hydrogen to water to make it, and this is the conjugate base because we took away a hydrogen to make it. So the acid always turns into the conjugate base, and the base turns into the conjugate acid in the course of an acid-base reaction. Let's look at another example. Ammonia, when it reacts with water, it produces NH4 plus and OH minus. In this example, identify the acid, the base, the conjugate acid, and the conjugate base. So notice that NH3, it gained a hydrogen, turning into NH4. So therefore, it's the proton acceptor, which means NH3 is the base in this example. Water lost the hydrogen. So water was the proton donor. It gave away a hydrogen, which makes it the acid. Now the base is always going to turn into the conjugate acid because we added a hydrogen to it. So NH4 plus is the conjugate acid, which means hydroxide has to be the conjugate base because water lost the hydrogen to make it. Now let's say if you're given water and you want to write the conjugate acid of water and at the same time the conjugate base. What is the conjugate acid of water? Whenever you want to find the conjugate acid of something, all you need to do is add H plus to it. So you're going to add a hydrogen and increase the charge by 1. So this is going to turn into H3O plus. The charge increases from 0 to 1. Now, whenever you want to write the conjugate base of something, take away a hydrogen and decrease the charge by 1. So instead of having 2 hydrogens, we now have 1, and the charge is going to decrease from 0 to -1. So the conjugate base of water is hydroxide. The conjugate acid is H3O+. So given ammonia, write the conjugate acid and the conjugate base of NH3. So the conjugate acid, we got to add a hydrogen. It's NH4 with a plus charge. To write the conjugate base, we need to remove a hydrogen, so it's NH2 with a negative charge. Now, for the sake of practice, try this one too. Let's say we have H2PO4-. Write the conjugate acid and the conjugate base. So we got to add a hydrogen. This will turn into H3PO4. So that's the conjugate acid of this thing. The conjugate base, we got to take a hydrogen and then decrease the charge by 1. -1 minus 1, that's -2. So now you know how to identify and how to write the conjugate acid and conjugate base of a substance. Now let's talk about the pH scale. I probably should have went over this earlier, but better late than never. So typically in most textbooks, you'll see the pH scale between 0 and 14. However, it can go beyond those numbers, so keep that in mind. At 7, the solution is neutral. At a pH that's less than 7, it's acidic. So if the pH was -2, it's very, very acidic. Above 7, the solution is basic. Now, if you want to calculate the pH of the solution, you need to know the concentration of the hydronium ion, or the H+ ions. It's negative log of H3O+. And the pOH of the solution, it's negative log of the hydroxide concentration. The pH plus the pOH always adds up to 14 at 25 degrees Celsius. Now, for some reason, if you ever need to find the H3O+ concentration, it's 10 to the negative pH. And if you need to find the hydroxide concentration, it's 10 raised to the negative pOH. So those are some equations that you might find useful when learning about acids and bases. Now, let's talk about strong acids and weak acids. You need to identify if an acid is going to be strong or if it's going to be weak. Strong acids ionizes completely. Weak acids, they partially ionize. They don't ionize completely. So a strong acid, basically, almost all of it would ionize in solution. A weak acid, less than 5%. Strong acids form strong electrolytes in water. The solution will conduct electricity. Weak acids form weak electrolytes when dissolved in water. So you need to know the 6 most common strong acids, and these are HCl, HBr, HI. HF is a weak acid. The others are nitric acid, HNO3, sulfuric acid, H2SO4, and perchloric acid, HClO4. Those are the most common strong acids that you'll see in a typical general chemistry course. Now, other weak acids include the ammonium ion, NH4+, acetic acid, and basically almost any acid that is not on this list. So like cyanic acid, nitrous acid, and sulfuric acid. Notice that sulfuric acid is stronger than sulfuric acid, and nitric acid is stronger than nitrous acid. What pattern do you see here? When dealing with oxyacids, the acid that has more oxygen atoms is the one that's going to be more acidic. So sulfuric acid is more acidic than sulfuric acid, and nitric acid is more acidic than nitrous acid. Perchloric acid is more acidic than chloric acid, which is more acidic than chlorous acid, and that is more acidic than hypochlorous acid. Now, HCl is not an oxyacid, so it doesn't fit this trend. In fact, HCl is more acidic than HClO, so keep that in mind. The trend only works for those that actually have oxygen. If it doesn't have oxygen, it's not going to fit the trend nicely. Now, you need to know how to write chemical reactions with strong acids and weak acids. We went over the example with HCl and water. Because HCl is a strong acid, it ionizes completely into chloride and hydronium ions. So notice that I have a single arrow. So that's the way you need to write the chemical reaction if you're mixing a strong acid in water. Now, if you're mixing a weak acid with water, it doesn't ionize completely. So you have a reversible reaction. So you need to use a double arrow symbol rather than a single arrow whenever you have a weak acid. But to identify the products is going to be very similar to the reaction above. So the only difference is just use a double arrow instead of a single arrow when dealing with weak acids because they exist in equilibrium. The reaction is reversible. Now let's talk about bases. You need to identify or distinguish a strong base from a weak base. Strong bases are soluble ionic compounds like potassium hydroxide, sodium hydroxide, barium hydroxide. These are soluble in water. They ionize virtually completely. Think of the strong acids like HCl, HBr, HI. The reason why they're strong is because they ionize almost 100%. So these are soluble, and as a result, they form strong electrolytes. And so they make strong bases. A weak base, the ones that have hydroxide in them, they're associated with insoluble compounds. Aluminum hydroxide doesn't dissolve very well in water. Only a small amount of it dissolves. And so it's insoluble. And it doesn't ionize. It ionizes less than 1%, which makes it a weak base. So I'm going to put here 100% ionization, less than 5% ionization. Some other examples of weak bases include ammonia and the conjugate bases of weak acids like fluoride, nitrite, acetate, cyanide. All of these are weak bases. Even HSO3-. Other examples of strong bases besides hydroxide are oxide. If you have oxide in solution, that's a strong base, and hydride. If you put an oxide ion in water, it's going to grab a hydrogen from water, creating two hydroxide ions. So oxide is a stronger base than hydroxide because it has less hydrogens. Hydroxide is a stronger base than water. Water is neutral. And water is a stronger base than H2O+ because H2O+ is acidic. So as you can see, the less hydrogens that are on an atom, the more basic it is. So oxide is more basic than everything else in this list, whereas H2O+ is most acidic. Hydride is also a strong base. When it reacts with water, it's going to produce hydrogen gas and hydroxide. So notice that hydride produces hydroxide. Typically, a stronger base will produce a weaker base, so hydride is a much stronger base than hydroxide. Let's talk about the mechanisms of these reactions. So this is oxide. It's basically an oxygen atom with 4 lone pairs. And I'm going to draw the Lewis structure of water. This oxygen has 2 lone pairs. So oxide is going to use one of its lone pairs to take a hydrogen atom from water. The arrow represents the flow of electrons. So this arrow tells us that this lone pair is going to be used to form a bond between the oxygen atom and the hydrogen atom. When the hydrogen atom breaks away from water, the two electrons in this bond is going to go back to the water, which is now going to be hydroxide. So this oxygen gained hydrogen, so now it looks like this. It lost a lone pair, so instead of having 4 lone pairs, it now has 3. And it no longer has a -2 charge, but it has a -1 charge. Now this oxygen, it lost a hydrogen, so now it has 1, but it gained a lone pair, as indicated by this red arrow. So now it has a -1 charge. So as you can see, whenever you mix oxide in water, if it's not bonded to anything, it's going to produce 2 hydroxide ions. Now let's consider this reaction where we said hydride plus water produces hydrogen gas and a hydroxide ion. So hydride is basically a hydrogen atom with a lone pair. So it's an ion in this case, and it's going to react with water. Now the hydride ion is attracted to this hydrogen, and the reason why it's attracted to it is because that hydrogen has a partial positive charge. It's partially positive because it's attached to a partially negative oxygen atom. Oxygen is electronegative, and as a result it pulls electrons towards itself. So as it pulls electrons towards itself, it leaves a partial positive charge on the hydrogen. And we know that opposites attract, so this hydrogen ion with a negative charge is attracted to this hydrogen atom with the partial positive charge. So those two will connect. And once they get together, this bond is going to break. Those 2 electrons are going to go back to this oxygen. So when these two get together, they form hydrogen gas, H2, leaving behind a hydroxide ion. So now this oxygen now has 3 lone pairs instead of 2. And so that's the mechanism for this reaction. So whenever you add hydride or oxide to water, it causes the solution to become basic. It produces hydroxide ions. Now let's briefly review some properties of acids and bases. Acids taste sour. If you think of lemons, lemons contain a lot of citric acid. They have a sour taste to them. Bases, on the other hand, they taste bitter. And if you ever were to touch a base, it would make your skin feel slippery. Now, with regard to indicators, acids, they turn blue litmus paper red. Bases, they turn red litmus paper blue. Now, we've covered the pH of acidic solutions. For an acidic solution, the pH will be less than 7. For a neutral solution, the pH is equal to 7. And for a basic solution, the pH is greater than 7. Now, both acids and bases can conduct electricity in solution. Strong acids are strong electrolytes, and the same is true for strong bases. They're strong electrolytes as well. They both ionize completely. Weak acids and weak bases are weak electrolytes. So if you were to place a strong acid or a strong base in solution, they would conduct electricity very well due to the free flowing ions in solution. Weak acids and weak bases, they don't ionize completely. Therefore, even though they can conduct electricity, they don't do it very well. So they can conduct a small amount of electricity in solution. So the electrical conductivity of a strong acidic solution is greater than the electrical conductivity of a weak acid solution. Now, acids, they react with active metals to produce hydrogen gas. A good example is this reaction. Zinc metal will react with aqueous hydrochloric acid to produce aqueous zinc chloride and hydrogen gas. Not all metals react with acids, only the active ones, such as zinc, aluminum, iron metal, nickel, sodium, but sodium is too reactive. It'll react with water as well. So any active metal will react with an acid to produce hydrogen gas. Copper is not an active metal. Copper doesn't react with acids. Silver, gold, those metals are not reactive. So copper, silver, gold, they don't react with acids to produce hydrogen gas. Now let's review some of the definitions of acids. Arrhenius acids, they release H+ ions in solution. Arrhenius bases release hydroxide ions in solution. Bronsted-Lowry acids, the definition for that is they're proton donors. Bronsted-Lowry bases are proton acceptors. And here's another one. Lewis acids are electron pair acceptors, but Lewis bases are electron pair donors. So those are some other definitions or ways of defining acids. Now let's consider the reaction between hydrofluoric acid and water. Hydrofluoric acid is a weak acid, so only a small amount of it will convert into the H3O+ ion, or the hydronium ion, and the conjugate base F-. Now this is a reversible reaction, so we need both arrows. The big arrow tells you that it's reactant favored. The small arrow tells you that only a small amount converts into the products that you see in the right, that is hydronium and F-. So that's an unequal reversible reaction. Now we can calculate the Ka of this reaction. Ka is the acid dissociation constant of the acid in question, which is HF. Now everything is in the aqueous phase except water. Water is a liquid. To write the expression of the acid dissociation constant, it's going to be the concentration of the products, which is H3O+ times F-, divided by the concentration of the reactants. Now, water is a liquid, so you don't include liquids and solids in the equilibrium expression when you're dealing with acids and bases. So that's Ka. As the Ka value increases, the strength of the acid increases. The pKa value decreases. So strong acids have large Ka values, but have small pKa values. Now, just as pH is the negative log of the hydronium ion concentration, pKa is the negative log of Ka. Now make sure you add these equations to your notes because we're going to use them later. Now let's say if we have a weak base. Let's use ammonia. Ammonia is going to react with water, but because it's a weak base, it's going to produce hydroxide ions in solution. Now ammonia being the weak base, as a Bronsted-Lowry base, it's the proton acceptor. It accepts a proton to turn into the conjugate acid NH4+. Water is behaving as a weak acid. It's donating the proton to ammonia, and so when it loses a proton, it turns into the conjugate base hydroxide. So this is the Bronsted-Lowry base, and this is the Bronsted-Lowry acid. This is the conjugate base, that's the conjugate acid. Now water can act as a base or an acid. We saw in the last example where HF reacted with water to produce H3O+ and F-. HF was the Bronsted-Lowry acid. It donated the proton to become the conjugate base fluoride. Water was the Bronsted-Lowry base. It accepted a proton to turn into the conjugate acid. So notice that water, depending on the circumstance, can behave as an acid, and sometimes it can behave as a base. Whenever you have a substance that can behave as an acid or as a base, that substance is known as an amphoteric substance. It can accept a proton, or it can give away a proton. So a good example of an amphoteric substance, or at least another example, in addition to water, is H2PO4-. This can act as a base. It can react with an acid like HF and become H3PO4, and then you get the fluoride ion. Or it can act as a base. Well, I take that back. Here it's acting as a base because that's acting as an acid. But in other circumstances, H2PO4 minus can act as an acid. If we react it with ammonia, it's going to become, we're going to get NH4 plus, and then dihydrogen phosphate will lose the hydrogen, turn it into monohydrogen phosphate. So here it's acting as the acid, ammonia is acting as the base. So this is another amphoteric substance. It can act as an acid or it can act as a base, depending on what it's reacting with. Now looking at the products on the right, which ones are conjugate acids and which ones are conjugate bases? HF lost a hydrogen. Anytime you remove a hydrogen from something, you create the conjugate base. Dihydrogen phosphate lost a hydrogen to become monohydrogen phosphate. So this is the conjugate base as well on the other reaction. Ammonia acquired a hydrogen to become ammonium. So this is the conjugate acid. And here, dihydrogen phosphate acquired a hydrogen to become phosphoric acid. So anytime you add an H plus ion to something, you create the conjugate acid. When you remove an H plus ion from something, you create the conjugate base. Now going back to the reaction above, let's write the expression associated with Kb, the base dissociation constant. Like Ka, Kb is going to be the products over the reactants. So we have the concentration of hydroxide times the concentration of ammonium rather. And we're going to divide that by the concentration of ammonia. So that's the equilibrium expression for Kb when you have a base reacting with water. Now, just as the pOH is equal to the negative log of the hydroxide concentration, pKb is equal to negative log Kb. Now here's another example that shows how water can behave as an acid and a base. Water can react with itself. I need to put a small arrow to the right and a big arrow towards the left. When you have pure water, it's not exactly pure water. A small amount of it will ionize with itself. One of the water molecules will act as the bronzolari acid, and the other one will act as a base. Now, if this acts as an acid, it's going to lose a proton. So it's going to turn into the conjugate base, hydroxide. If this acts as a base, it's going to acquire a proton, turning into the conjugate acid, hydronium ion. Now, hydroxide and H2O+, they're dissolved in water. So they're aqueous, but water is a liquid. Thus, the equilibrium expression for this reaction is not Ka or Kb, but it's Kw. It is the auto-ionization constant for water. It's equal to the concentration of the products divided by the concentration of the reactants. But because both reactant are in a liquid state, we just divide it by 1. So we could simply write it like this. Now Kw is an equilibrium constant that is dependent on temperature. If you increase the temperature, Kw increases, which means more of the water molecules will ionize into these ions at higher temperatures. At lower temperatures, these ions convert back to the liquid form, but at higher temperatures, they will ionize more into these two. Now at 25 degrees Celsius, Kw is 1 times 10 to the negative 14. But if you were to increase the temperature to, let's say, 60 degrees Celsius, Kw increases. It's 1 times 10 to the negative 13. So it's dependent on temperature. But for most chem problems, if you don't see a temperature, it's assumed to be 25 degrees Celsius. So thus we have this equation. Hydroxide times H3O plus is equal to 1 times 10 to the negative 14, which means if you know the hydronium ion concentration, you could use that formula to calculate the hydroxide ion concentration. Because of that formula, the pH plus the pOH adds up to 14. Likewise, the pKa plus the pKb at this temperature adds up to 14 as well. So those are some additional formulas that you want to add to your list of formulas in your notes. Now there is another one that we can add as well. Since hydroxide times H3O plus is equal to 1 times 10 to the negative 14 at 25 degrees Celsius, it turns out that Ka times Kb, it's also equal to Kw, which at 25 degrees Celsius, that's 1 times 10 to the negative 14. So if you know the Ka value, you can easily calculate the Kb value. And remember, the pKa is a negative log of Ka. So if you have the Ka value, you can calculate the pKa value. And then if you have the pKa value, you could use this equation to get the pKb value. So there's a lot of equations that you could use to find one thing from another. Now let's work on some practice problems. The H3O plus concentration in a solution is 4 times 10 to the minus 3. What is the pH of the solution? We know that the pH is equal to negative log of the H3O plus concentration. So that's going to be negative log 4 times 10 to the negative 3. Now without a calculator, if you were to estimate the range of the pH value of this solution, what would you say? Looking at the exponent, which is negative 3, the pH is going to be somewhere close to 3. Would you say it's going to be 2 to 3 or 3 to 4? It's always going to be the lower of the two ranges. So it's going to be between 2 to 3. Now let's plug it in to get our answer. Negative log of 4 times 10 to the minus 3, it's 2.3979. So that's going to be the pH of the solution. So we could say it's approximately 2.4. Now let's calculate the pOH of the solution. The pH plus the pOH adds up to 14. So if you rearrange the equation, the pOH is going to be 14 minus the pH. So 14 minus 2.4. 14 minus 2 is 12. 12 minus 0.4 is 11.6. So the pOH is going to be 11.6. Now what about part C? What is the hydroxide ion concentration of the solution? To calculate the hydroxide ion concentration, we could use this formula. It's 10 raised to the negative pOH. So that's 10 raised to the negative 11.6. So that's going to be approximately 2.5 times 10 to the negative 12, and the unit will be molarity, or moles per liter. So that's the hydroxide ion concentration of this solution. Number 2, the hydroxide concentration in a solution is 5.3 times 10 to the negative 4. What is the pOH of the solution? By the way, feel free to pause this video if you want to try this problem. The pOH is going to be negative log of the hydroxide ion concentration. And so that's going to be negative log 5.3 times 10 to the negative 4. So if you were to estimate the range of the pOH of the solution, what would you say? So looking at this exponent, negative 4, we know it's going to be between 3 to 4. Now let's go ahead and plug it in. The answer is going to be 3.2757. So we could say that it's approximately 3.28. Now let's calculate the pH of the solution. The pH is going to be 14 minus the pOH. So that's 14 minus 3.28. 14 minus 3 is 11. 11 minus 0.28. If you were to take 100 and subtract it by 28, you would get 72. So this is going to be 10.72. Now let's move on to part C. What is the H3O plus ion concentration of this solution? So we could use this formula. It's 10 raised to the negative pH. So it's going to be 10 raised to the negative 10.72. And that answer can be rounded to 1.9 times 10 to the negative 11. So that's going to be the concentration of H3O plus in the solution. Now what about this one? We're given the hydronium ion concentration and we want to calculate the hydroxide ion concentration. Feel free to try this problem. So if you recall, H3O plus times the concentration of OH minus, that's going to be equal to Kw, the auto ionization constant of water. And at 25 degrees Celsius, it's 1 times 10 to the minus 14. So to get hydroxide by itself, we need to divide both sides by H3O plus. Thus, the hydroxide ion concentration is going to be Kw, which is this, divided by H3O plus. So it's 1 times 10 to the negative 14 divided by 2.5 times 10 to the negative 5. So the hydroxide concentration is going to be 4 times 10 to the negative 10. So that's the answer for number 3. Number 4. If the Ka of acetic acid, HC2H3O2, is 1.8 times 10 to the negative 5, what is the pKa of the acid? Now just as pH is negative log of H3O plus, pKa is negative log of the acid dissociation constant, which is Ka. So it's going to be negative log of 1.8 times 10 to the negative 5. So looking at the exponent, we know this is going to be between 4 to 5. So the pKa is 4.745. That's the pKa of acetic acid. Now let's calculate the pKb, and then we'll calculate the Kb. Just as pOH is 14 minus pH, pKb is going to be 14 minus the pKa at 25 degrees Celsius. We're going to assume it's that temperature unless specified otherwise. So this is going to be 14 minus 4.745. Now let's see if we could do this mentally. 14 minus 4 is 10. If you were to subtract 1,000 by 745, what would you get? You should get 255. So 10 minus 0.75 is going to be 9.255. So we're going to round it and say, well actually this is a good round answer. When you plug it in, you actually get 9.25527. So we'll stick with that answer. Now let's get Kb. So Kb is 10 raised to the negative pKb. So that's going to be 10 raised to the negative 2.55. The final answer is going to be 5.56 times 10 to the negative 10. So that's the value of Kb. And remember, Ka times Kb is equal to Kw. So you can get Kb by taking Kw and dividing it by Ka. So Kw is 1 times 10 to the negative 14. Ka is 1.8 times 10 to the negative 5. And this will give you the same answer, 5.56 times 10 to the negative 10. So that's it for number 4. Number 5, which of the following statements is false? So let's analyze each one. Let's focus on A. Bases taste bitter and feel slippery. That's a true statement, so we can eliminate that answer choice. Now looking at B, acids taste sour. If you think of an acid like lemon, lemon tastes sour, and acids react with active metals to produce hydrogen gas. So if we were to take an active metal like iron, and if we were to react this with hydrobromic acid, this would form FeBr2 plus hydrogen gas. The hydrogen gas will escape the solution. So active metals like zinc, iron, aluminum, they can react with strong acids to produce hydrogen gas. So B is a true statement. Now what about C? HCl is a strong electrolyte. This is true. If you were to dissolve hydrochloric acid in water, because HCl is a strong acid, it will dissociate almost completely into these ions. And whenever you have free-flowing ions in solution, it can conduct an electric current. So what we have here is a strong electrolyte. Strong acids are strong electrolytes. Strong bases are also strong electrolytes. Now what about D? Acids turn red litmus paper blue. Now this is not correct. This is a false statement. The reverse is true. Acids turn blue litmus paper red. So D is the false statement. As for E, sodium hydroxide is a strong base, like HCl is a strong acid. Both of them are strong electrolytes, and they both can conduct an electric current. Therefore, E is a true statement. So answer choice D is the correct answer for this problem. Number 6. Which of the following solutions will have the highest pH? Is it going to be HBr, hydrobromic acid, HF, hydrofluoric acid, NaCl, NH3 ammonia, or KOH, potassium hydroxide? What would you say? Well, first, let's identify each substance. Hydrobromic acid is a strong acid. Hydrofluoric acid is a weak acid. NaCl is a neutral salt. NH3 is a weak base. KOH is a strong base. Now let's create our pH scale. So we're going to put 7 in the middle, 0 on the left, 14 on the right. A 0.1 molar solution of hydrobromic acid, it's going to have a pH of around 1. So I'm going to put HBr here. Now, a weak acid like HF, the pH is going to be somewhere around 2 to 3. Sodium chloride is neutral, so the pH is going to be 7. Now keep in mind, acids have a pH that's less than 7. Now, because HBr is a stronger acid than HF, given the same concentration, HBr is going to produce a solution with a lower pH. So the strongest acid is going to have the lowest pH, assuming the concentration is the same. Now what about the bases? Here we have a weak base and a strong base with the same concentration. This solution is going to have a pH of around 11. A 0.1 molar KOH solution will have a pH of around 13. So this is going to be NH3 and then KOH. But what you want to gather from this is that the strong base is going to have the highest pH. The strong acid is going to have the lowest pH. So remember, bases have a pH that's greater than 7, acids have a pH that's less than 7. Thus, because we're looking for the solution with the highest pH, we're looking for the solution with the strongest base, given that their initial concentration is the same. Therefore, answer choice E is the correct answer. Number 7. The Ka value for HF and acetic acid are 7.2 times 10 to the negative 4 and 1.8 times 10 to the minus 5. Which acid is stronger? Hydrofluoric acid or acetic acid? What would you say? Well, first, let's write down our two acids on the board. So we have hydrofluoric acid and acetic acid. And let's write down their corresponding Ka values. Now, as the Ka value increase, what's going to happen to the strength of the acid? Does the acid strength go up or down? You need to know that acid strength is directly related to Ka, which means that the acid with the higher Ka value is the stronger acid. So which one is higher, -4 or -5? On a number line, -4 is higher than -5. The higher numbers are to the right, and -4 is here, and here's -5. So you can see -4 is to the right of -5 on the number line. Therefore, HF is the stronger acid. So even though both of these acids are considered weak acids in general, this acid, HF, is stronger than acetic acid. It's a stronger weak acid. Now what about part B? Which conjugate base is stronger? The conjugate base for HF is fluoride. The conjugate base for acetic acid is acetate. So which one is stronger? So here's what you need to know. The stronger acid creates the weaker conjugate base. And the weaker the acid, the stronger the conjugate base. So because HF is the stronger acid, the base is going to be weaker. So because C2H3O2, or acetic acid, because this is the weaker acid, the conjugate base is going to be stronger. And here's why. Ka times Kb is equal to a constant, Kw. Kw doesn't change if the temperature stays constant. Therefore, if you increase Ka, Kb is going to decrease. Just as Ka reflects the acid strength, Kb reflects the base strength. This one has a higher Ka value. This is going to have a higher Kb value. Let's calculate the Kb value for each conjugate base. So it's going to be Kw, or 1 times 10 to negative 14, divided by that number. And so for fluoride, the Kb value is going to be 1.39 times 10 to negative 11. Now let's do the same for acetate. If we take 1 times 10 to negative 14 divided by 1.8 times 10 to minus 5, we're going to get this familiar value, which we calculated in an earlier problem, 5.56 times 10 to negative 10. 10 to the negative 10 is higher than 10 to the negative 11. Therefore, because acetate has a higher Kb value, it's going to be the stronger base. So remember, the stronger the acid, the weaker the conjugate base. HF is the stronger acid, fluoride is the weaker conjugate base. This has a higher Ka value, so it's going to have a lower Kb value for the conjugate base. Here, this is the weaker acid, but this is going to be the stronger conjugate base. As you decrease the Ka value for an acid, the Kb value for the conjugate base increases. So they're inversely related, so to speak. Now let's talk about the pKa. Which acid will have the lower pKa value? Is it going to be HF or acetic acid? Now remember, pKa is equal to the negative log of Ka. So because of that negative sign, there's an inverse relationship between Ka and pKa. Acid strength increases with high Ka values, but it increases with low pKa values. So the acid with the low pKa value is the stronger acid. And let's calculate pKa. So let's take the negative log of that number. Negative log of 7.2 times 10 to negative 4 is 3.14. So this is the pKa value. I'm just going to write the number. For HF, it's 3.14. Now the pKa value for acetic acid, if we take negative log of 1.8 times 10 to the minus 5, we get this familiar value. It's 4.74. It's 4.7447, so you can round it to 4.74 or 4.745. Now notice that the stronger acid has the lower pKa value, whereas the weaker acid has the higher pKa value. Therefore, acid strength and pKa are inversely related. Acid strength increases with decrease in pKa values. So let's summarize what we've learned here today. The stronger acid is going to have the higher Ka value, and the stronger acid is going to have the lower pKa value. So just keep that in mind. And the stronger the acid, the weaker the conjugate base. Now let's work on this exercise. Go ahead and match each term with the correct letter. So let's begin by focusing on the Arrhenius definition of acids and bases. So what is the Arrhenius acid? An Arrhenius acid is an acid that releases H+ ions in solution. So number 1 is C. The Arrhenius base releases hydroxide ions in solution. So number 2 is E. Now what about the Bronsted-Lowry definition of acids and bases? What can we say about that? The Bronsted-Lowry acid is a proton donor. The Bronsted-Lowry base is a proton acceptor. So number 3 is B, number 4 is F. Now, for the Lewis definitions, or the Lewis definition of acids and bases rather, it has to do with a transfer of electrons. A Lewis acid is an electron pair acceptor. A Lewis base is an electron pair donor. So number 5 is A, number 6 is D. Now, let's go ahead and talk about this. So to understand it from the Arrhenius point of view, imagine if we have hydrochloric acid. Hydrochloric acid in water can dissociate into hydrogen ions and chloride ions. So HCl releases hydrogen ions in solution, which makes it an Arrhenius acid. Now let's consider a strong base like sodium hydroxide. Sodium hydroxide can release hydroxide ions in solution. So that makes it an Arrhenius base in that reaction. Now, let's focus on the Bronsted-Lowry definition of acids and bases. Let's say if we have HF reacting with water, where we're going to get fluoride and H3O+. HF is the Bronsted-Lowry acid. I'm just going to write acid because it donates a proton to water in order to become fluoride. So as HF becomes fluoride, it loses a proton. It donates a proton. So the proton donor is the Bronsted-Lowry acid. Water in this reaction is acting as the Bronsted-Lowry base. Water accepts a proton from HF, and as it absorbs that proton, it turns into the hydronium ion H3O+. So a proton acceptor is a Bronsted-Lowry base. Now let's consider an example that highlights the Lewis definition of acids and bases. So for this example, we're going to use aluminum chloride, and we're going to react it with ammonia, NH3. Ammonia has a lone pair, and as it donates that lone pair to aluminum, a bond is going to form between aluminum and the nitrogen atom. And so we're going to get a product that looks like this. Whenever aluminum has 4 bonds, it's going to have a negative formal charge. And whenever nitrogen has 4 bonds, it will have a positive formal charge. But notice that ammonia donates a pair of electrons to become this product. Because it donates a pair of electrons, it is the Lewis base. And we know that ammonia is a weak base, but in this reaction, it's the Lewis base. Therefore, the electron pair donor is the Lewis base, so 6 is D. The aluminum in AlCl3, it accepts a pair of electrons, and that makes it the Lewis acid. The Lewis acid is the electron pair acceptor. By the way, if we were to put sodium chloride in water, the pH of the solution will be 7. This is what is known as a neutral salt. But if we were to put aluminum chloride in water, the pH is not going to be 7. The pH is less than 7. So this is what is known as an acidic salt. Whenever you have a metal with a very high positive charge, that metal has a strong affinity for electrons. It's going to be a Lewis acid, an electron pair acceptor. And so it could bond to water in such a way that it can split hydrogen and hydroxide from water. It'll absorb the hydroxide, releasing hydrogen ions in the solution. So when you see metal ions with very high positive charges, like Al3+, Fe3+, or even Pb4+, these strongly positively charged ions are acidic in nature. Acids tend to have positive charges. Bases tend to have negative charges or a lot of lone pairs. Here, this is a neutral base with a lone pair, and here, this has a negative charge but a lot of lone pairs. Keep in mind, lone pairs represent electrons, which are negatively charged. So acids are associated with positive charges. Bases are usually associated with negative charges.